In this video, you and I get to take a look at some traditional methods for using a service provider, and we'll compare and contrast those methods against MPLS Layer 3 VPNs. Let's jump in. Here are the opt-out questions for this video. So if you read these and you're already comfortable with all these concepts, hey, join me in the next video. Otherwise, you and I are going to take a closer look at the components and the architecture that goes into an MPLS Layer 3 VPN solution. Let's begin. I'd like you to go back with me in the time machine, back to the 1980s. And back then, if we needed permanent, always up, site-to-site connectivity of some type, let's say we had a site in Southern California and a site in Northern California, and we want to tie them together, it's very likely we'd use a leased line. So we'd have a circuit that goes between point A and point B. Now the circuit is just a circuit. We would likely use a serial interface on one end, and then very likely point-to-point protocol for layer 2. And then we were in charge of whatever IP address space we wanted to put on top of that. So if we wanted to call this link 10.0.0.0/24, and maybe over here we had the 172.16 and 192.168 on the other side, and then we have a routing protocol, we're all good. We simply have a circuit that we can go ahead and use for our connectivity, and we pay for it 24/7. Now, as we move to the 90s, I remember being at Paramount Pictures when Paramount was starting to migrate from their leased lines over to Frame Relay. And Frame Relay is like, oh, it's amazing because it costs less and it's more flexible. And with Frame Relay, we would also get this circuit. But instead of being an actual leased line, it's actually a permanent virtual circuit. So we have the service provider cloud. And what the service provider is guaranteeing us is that, let's say we purchased a committed information rate of 64K or T1 speed or whatever we wanted to purchase. They would guarantee that anything we shot in this end of the circuit would come out that end of the circuit, and it would happen at least at the throughput that we're purchasing from that provider. And we'd use things like data link connection identifiers to identify the virtual circuit at both ends. And we'd also be using serial interfaces, but the encapsulation would be Frame Relay. And very similar to a leased line, we're also responsible for the IP address that we're going to use for that link from point A over to point B. So the customer in both cases is totally responsible for their layer 3 addressing and managing their own routing. Now let's say we have two sites that are connected either to a large service provider or the internet. They'll both serve for this example. So we've got some connectivity from the customer to this cloud, to this network. And maybe this customer at site 1 has the address of 23.1.2.3, and at site 2 it has the IP address of 44.1.5.9. Now that they have connectivity, and if this is the internet, these would be globally routable addresses, what the customer could do is they could overlay a virtual network on top of the existing network. So this is an example of IP over IP. For example, generic routing encapsulation could be used. And this red network here between site 1 and site 2, although it's on top of an existing IP network, we could have a logical network, for example, the 10.0.0.0 network. And that's a private network. Now, it's not encrypted yet. We can take a look at that in a moment. But it is private from the perspective that it's only relative to site 1 and site 2. So through this GRE tunnel, we could run a routing protocol. And Acme Site 1 could advertise its networks, and Acme Site 2 could advertise its networks over this GRE tunnel, this logical virtual network that we've created as an overlay on top of the service provider or on top of the internet, and they could have connectivity that way. Now the challenge is, whenever we're using somebody else's network, like the internet or a service provider, with some type of an IP over IP tunneling protocol like GRE, we probably also want to throw on top of that some security to encrypt the packets as they're being sent over this virtual network. So by adding IPsec, just for security purposes, anybody in this network who's eavesdropping won't be able to determine what the actual payload is of our packets, because the people in the middle, if they're eavesdropping, won't have the secret key to unlock that data. So we'll use a shared key at site 1 and site 2, and only those two sites will have the keys to encrypt and decrypt, to lock and unlock the data. Anyone in the middle is out of luck. And here's what I want to point out with all these scenarios, is that the customer is in total control of all their routes. With a leased line, a virtual circuit, or an overlay technology like GRE, the customer is deciding what IP addresses to use on the link itself, or in this case, the GRE network itself. And then if they want to, they can run a routing protocol and share the routes from one site to the other for full reachability. So in our discussion of then, now, and the future, I would say that's a lot of then and a little bit of now of what's occurring with network connectivity. The leased lines, because they are so expensive, are out of favor, or moving out of favor, and frame relay as a wide area network technology. Now, we still might see it quite a bit, for example, just to get connectivity to a service provider. For example, this could be a frame relay connection right here. If we've already got the circuits in place and we've got the bandwidth, we may be using frame relay just as a technology to get to a bigger network and have an IP address associated with us as we connect to that network, instead of using frame relay as a virtual circuit technology from one site to a remote site. Now, as you and I take a look at MPLS Layer 3 VPNs, the game changes significantly. So let's take a look at how an MPLS Layer 3 VPN application might work for providing WAN connectivity between multiple sites. So let's say, for example, you and I are the service provider, everything in this larger gray rectangle, and we have some customers. We have Acme at site 1, and we have Acme over at site 2. And we've also got CBT at site 1 and CBT at site 2. And they have a boatload of networks. Now, the trick is this. Any of the routes that Acme wants to have and advertise, we need to make sure we propagate those routes over to Acme Site 2. So we have to build the control plane to advertise routes. And let me ask you a question. What would happen if the 172.16 address space that Acme has, what would happen if we accidentally advertise those routes down to CBT, not the same customer, by accident? What would happen? Well, if they have a route to 172.16, when the customers at this site send traffic to 172.16, it's going to be forwarded up to Acme, and we're going to have a mingling of traffic. So as a service provider, if we want to keep our jobs, we need to keep Acme's routes separate from CBT's routes, and CBT's routes separate from some other customer that we have. So the control plane is all about advertising the correct routes to the right customers. So I'd like to walk you through the process of the control plane inside of an MPLS Layer 3 VPN. The first thing we need to do is somehow take the routes that Acme has from Site 1, and we need to learn them. And that's a significant difference from these other technologies that we looked at. With an MPLS Layer 3 VPN, we are going to run a routing protocol between the customer edge, for example right here, and the provider edge. And that routing protocol could be, you name it. Let's say OSPF or EIGRP if they're both Cisco devices. We could even run BGP. As long as we're sharing the routes back and forth, that's the first significant difference with using MPLS Layer 3 VPNs. The customer and the provider edge are peering. They're actually sharing routing information with each other. And the method they use is a routing protocol. Let's say we have that route being advertised. 172.16 is being advertised to the PE, the provider edge router. Now, here's a really important challenge that R1 needs to deal with. R1 needs to take that route of 172.16 and it needs to keep it private. It needs to keep that associated just with Acme as opposed to CBT. So to do that, we're going to use a special method called a VRF. VRF stands for Virtual Routing and Forwarding. And when you see VRF, I want you to think of a mini router that's living inside the host. For example, many of us are familiar with virtualization. For example, we may have a PC. And then we may run some software like VirtualBox or VMware Workstation. And we can run virtual PCs inside of that. So this could be PC1, PC2, PC3, all virtualized inside of that. Well, a VRF is like a virtualized router. So R1, for example, could run two little virtualized routing instances, and it could allocate one of those VRFs for Acme Site 1. So this interface that goes off to Acme Site 1 and a little space in memory for all those routes and so forth as part of the VRF allows R1 to keep the routes learned from Acme Site 1 separate from the routes learned from CBT Site 1. Because the routes coming in from CBT at Site 1 would be learned inside of an interface that's part of a different VRF, a VRF just for CBT. So a VRF is a virtual routing and forwarding instance, and a router can have several of them. Now, if you're not using VRFs at all, like just a traditional straight-up IPv4 router, you're going to have one global routing table. When we start adding VRFs, each of those VRFs is going to have its own routing table just for that VRF. So routes that we learn from Acme Site 1 are going to be confined, if you will, or logically kept inside of Acme's VRF. Now, the ultimate goal of building a control plane and advertising routes is so that we can get that route of 172.16 over here to Acme Site 2. We don't want to advertise this network from Acme Site 1 down to CBT Site 1 or down to CBT Site 2. We only want to advertise it to the right place. So now that R1 has this network, 172.16, and it's in the VRF for Acme on R1, how in the world does it get that route advertised over to R5, who can then advertise it up to Acme Site 2? And the answer is we are going to use a school bus. So I'm going to go ahead and draw a little bus here. There's the windshield, there's the windows. And we're going to use that school bus as a transport mechanism to build the control plane so that R1 can tell R5 about the routes that it's learned from Acme Site 1. So to do that, what happens is R1 is going to take those routes out of the Acme VRF, that virtual routing and forwarding instance, and it's going to put those into the school bus. Now, in the process of putting it into this transport mechanism, the school bus, these routes, there's going to be a lot of information added to those routes that identify that, hey, this route came from Acme Site 1. It's part of Acme's virtual private network space. And when that information is added, for example, things like route distinguishers and route targets that we will talk about in detail in an upcoming nugget, once we identify all those details about where this route came from, it magically becomes something called a VPN route. And more specifically, we could call it a VPN v4 route. Or you could call it an IPv4 VPN route. But all a VPN v4 route is that route that came in from Acme. It has all the extra baggage identifying that, hey, this came from this customer. There's also some identification inside of that route that keeps the 172.16 from Acme 1 very different from the 172.16 coming from CBT 1. That's done with something called a route distinguisher. But once we add all of that baggage, all those tags, if you will, that is now called a VPN v4 route or a VPN route. And the bus is going to deliver that route over to R5. Now this bus, this transport mechanism that's delivering these VPN v4 routes is called, you ready for it? Multi-protocol BGP. And why do they call it multi-protocol BGP? It's because we're not just carrying IPv4 routes. Multi-protocol BGP has the ability to carry additional routes, such as VPN v4 routes, with all those additional tags and information regarding where that route came from, what customer it belongs to, and eventually where it should be delivered. And so what happens is R1 and R5, the two PEs inside of our service provider network, we are going to have a BGP neighborship, an internal BGP neighborship supporting multiple protocols, including VPN v4 routes. And that's how R1 gets all of that detail about this customer's route over to R5. Now guess what? Over on R5, it also has information regarding VRFs and which interfaces belong to which VRFs. So what R5 is going to do, R5 is going to extract that VPN v4 route. Again, we're talking about the control plane. We're building routing tables. It's extracting that route from BGP. It looks at all those details that have been attached to that route. It identifies that, oh, I need to forward this route up to Acme at Site 2. It strips off all of that additional detail and simply does a route advertisement regarding 172.16.00/12 or whatever networks are being advertised up to Acme at Site 2. So this also implies that R5 and Acme at Site 2, they are also running some type of a routing protocol to exchange routes. It could be either OSPF or some other IGP, or it could even be Border Gateway Protocol. It really doesn't matter. We're just doing normal IPv4 routing between the provider edge, R5, and the customer edge. In this case, it's Acme at Site 2. And that, my friend, is the control plane of an MPLS Layer 3 VPN. So as a quick highlight of the important pieces here in this architecture is that we have a routing protocol between the customer edge and the provider edge on both sides. We are going to be running multi-protocol BGP between R1 and R5, between our PEs in our environment. In a huge environment, we'll probably scale that with something called a route reflector, so we don't have to have a full mesh of all of our PEs. But the concept is the same. We're going to learn BGP information from our PEs inside of our company to other PEs inside of our company. We have the VRFs associated on each of the PEs to keep our customer routes separate and effectively private from the other general routes that might be in the routing table on R1 and on R5. And the reason that this VPN v4 route is considered to be a virtual private network route, the private part, is the fact that we are not going to advertise Acme's 172.16 network over to CBT Site 2 or CBT1 Site 2. We're only going to deliver it to the appropriate site. In this example, it would be Acme at Site 2. And that, my friend, is what makes the P the private portion of an MPLS Layer 3 VPN. We aren't doing any encryption on this traffic inside of our service provider network. So we're not talking about IPsec. We're just simply talking about keeping Acme's routes separate and private from our other customers' routes. Now, once this is set up and the control plane has been built for connectivity, for example, from Site 2 to 172.16, and vice versa, by the way, the 192.168 from Site 2 would be advertised down to R5, and the advertisement in the VPN v4 route would be advertised in the other direction as well. And once the control plane is built, then we have the possibility of transit traffic, which is also referred to as the data plane, being successful. So, for example, if Bob at Site 2 of Acme wants to go ahead and ping 172.16.0.90 or some other host over here on the 172.16 network, the data plane should take Bob's transit traffic. It should be forwarded through the service provider network and be routed up here to this network instead of to some other customer's 172.16 network space. Now, some of the magic involved in making this all happen are labels, MPLS labels. For example, when this network right here, 172.16, gets advertised into R1 as part of the VRF, and it gets exported into BGP for transport over to R5, one of the things that's going to be added or tagged on to that VPN v4 route is a label. So, for example, R1 will take some label that's not currently in use. Let's say that 128 is available as a local label on R1. He'll associate that with the VPN v4 route, and they often call that the VPN label. So that VPN label is part of that extra baggage, if you will, that tag on information that identifies that VPN v4 route, and R5 is going to remember that as part of the control plane. And here's what you and I are going to do. As we take a look at implementing these individual components, for example, the VRFs and the BGP, we'll take a look at how those labels are being added and how they operate as we progress together. For now, our primary objectives that I wanted to share with you are the details on how customer edges and providers share routes, which is through a routing protocol, what makes a VPN v4 route private, the fact that it's not shared with other customers or unauthorized sites that shouldn't be learning about that route, the fact that we have VRFs for each customer to keep those routes separate locally on the PE routers, and the fact that the PE routers are going to use BGP, specifically multi-protocol BGP, to carry that VPN v4 routing information between the PEs. For this last one, SDN, I often think of George Jetson. At Spacely Sprockets, George's job was to push the button, and that's all he did. And then everything magically happened as a result of him pushing that button. Well, with software-defined networking, one of the results we can hopefully achieve with that is automation. For example, let's say we have a user called Bob, and Bob is sitting at a PC which is connected to a switch, which is connected to a router, which is connected to another switch, which is connected to another router and goes to another network, and that cloud is connected to, for example, Mary. And so if Bob and Mary are having a real-time conversation, we definitely want to have some quality of service across this network for their conversation. And what happens if we have like 30 or 40 additional users who all have various needs on the network? Now, hopefully, we've designed and configured the quality of service to identify the traffic and mark it and give it preferential treatment at various points in the network to make those applications, such as voice over IP, a viable application that actually works and is acceptable, because Bob can hear Mary and Mary can hear Bob, and it works. Well, with software-defined networking, we would have intelligence in the network to the point where it could identify the flows of traffic and automatically tune and tweak the network to prioritize that type of traffic if that was our desired goal. Again, we'd have that red button, we'd push it, and our software-defined network would automatically change the configuration to support that type of flow. Does it sound like a dream? And the answer is, it is a dream. And at some point in the future, as we have intelligent applications managing the control plane and changing dynamically the configuration on the hardware, which is what software-defined networking is all about, it'll be a wonderful thing. And perhaps through software-defined networking, multiple vendors will work together for integration. But the moment that came out of my mouth, I also remember that these vendors like Juniper and HP and Cisco, they're all very competitive with each other. So it might be called like co-opetition. They'll cooperate because they have to, but at the same time they want to have their proprietary value adds so that the customer continues to buy their product. So we shall see what software-defined networking brings to the table as the years roll on. Now in the meantime, while we're waiting for SDN, if we want quality of service, for example between Acme Site 1 and Acme Site 2, we, being the service provider, are going to have to make that happen. We can't rely on an application that's going to do it for us. We're going to have to configure that. And we'll do that in the intermediate and advanced MPLS courses with a technique called traffic engineering. And as I mentioned, if we were using software-defined networking, we could just hit that red button and say, boom, we need QoS of this type, and it would just happen. And until that day, until we get that magic button, we are going to have to implement the configuration on these devices to support that quality of service through traffic engineering on an MPLS network. I have enjoyed our time together, and I'm glad that you joined me for this video. I hope it's been informative for you, and I'd like to thank you for viewing.